Okay, welcome to the last lecture of today's afternoon. I'm very happy to introduce Carolina Araujo from IMPA. Besides being a great mathematician and a great lecturer, you will see, she's one of these persons who are working so hard for us to be in this fantastic ICM. Carolina.
Thank you, Alicia, for the introduction. So I would like to thank the program committee for giving me the honor of speaking at the ICM here in Rio. Today I'm going to be talking about positivity and algebraic integrability of holomorphic foliations. So first I will tell you the origins of holomorphic foliations and how they became an important tool in birational geometry. And then I will also discuss a series of results in a long research and collaboration with Stéphane Druel. So let's start with the origins. So the origins of the theory of holomorphic foliations are in algebraic differential equations in the plane. So this goes back to the 19th century and works with Darboux, Poincaré, Pinlevé, and others. And one of the key and central problems in the theory was to find conditions to guarantee that a certain algebraic differential equation has algebraic solutions. So let me give you two examples. So these are two nice-looking algebraic differential equations, and they can be easily integrated, and their solutions are described as follows. So notice that for the first algebraic equations, the solutions are algebraic. They're just lines through the origin. They're functions that correspond to lines through the origin. While in the second case, the solutions is transcendental. And let me now put some geometry in this picture so you can also interpret and look at these differential equations from the geometric point of view. So at a general point of the plane, the equation gives you a tangent direction at that point. And the solutions correspond exactly to curves that are everywhere tangent to this field of directions. So if you think of this way, then an algebraic differential equation of this kind give you a subsheaf. You can think of this as a subsheaf of the tangent bundle of the plane. And then now, instead of looking at situ, let's extend and saturate this distribution, and then you get a saturated subsheaf of the tangent bundle of Pezzo. And now you start to see a fundamental difference between these two examples. So while the first one, this subsheaf is O1, the second one is just O. And notice that for the first one, this is an ample subsheaf of the tangent bundle. And this is probably the simplest, the simplest manifestation of the phenomenon that I want to describe in this lecture. And as we will see, the ampleness of this subsheaf is what is forcing the solutions of the algebraic equation to be algebraic, or the curves, which are called the leaves of the foliation, to be algebraic. Okay, so let's now generalize this. So what I explained were examples of foliation by curves in the plane, but we can generalize it to higher arbitrary rank and dimension. So we start with a complex projective manifold X. So most of the theory that I'm going to be describing can be extended to the singular setting, but I just want to convey the ideas here. So unless stated otherwise, I will be always working on a complex projective manifold whose dimension I will always denote by n. Sometimes I may forget to write this. So a foliation is a saturated non-zero subsheaf of the tangent bundle satisfying Frobenius integrability condition, that is, that it's closed under the Lie bracket. So this condition guarantees that if you take a general point of X, then you can find an analytic submanifold of X whose tangent bundle is precisely the restriction of F. So if you take these analytic submanifolds to be maximal when connected, then what you get is what we call a leaf of the foliation. So these are the leaves. There are maybe some points, so I'm looking at the subsheaf, so there may be some points where F is not a subbundle of the tangent bundle. So this set is what we call the singular set of the foliation. And we are going to come back to that later. Okay, so let me give you the simplest example of foliation. So you can take any dominant rational map with connected fibers, and then you can restrict to the open subset of X where this map is a smooth morphism and consider the relative tangent bundle, and then you can extend and saturate it to get a foliation on X. And so in this case, the leaves are just the fibers of the rational map. And so this is what we call an algebraically integrable foliation. And so as an algebraic geometry, I feel more comfortable working with algebraically integrable foliations. But it also turns out that for applications in birational geometry, one important feature is, an important problem is to find conditions that guarantee that a certain foliation is algebraically integrable. Okay, so let me describe a nice example where this idea appears. And so this is the Miyaoka's criterion of uniruledness. So Miyaoka proved that the following characterization of uniruledness. So either a variety, a manifold X is uniruled, and that means that through any point of X you can find a rational curve, or for a general complete intersection curve on X, the restriction of the cotangent bundle of X to this curve is NIF. And it turns out that algebraic integrability of foliations, and in this case the description of the algebraic leaves, play a key role in Miyaoka's proof. And the ideas and this criteria have been generalized, and here I'm mentioning a few authors, Bost, Bogomolov, McQuillan, and more recently the work of Campan and Palm. So I'm going to try to explain this in the next slide. Okay, so let me start with the following setup. Let me remind you about the Harder-Narasimhan filtration. So we start with an n-dimensional, say, complex projective complex manifold and an ample divisor on X. So if you have this, then you can define a notion of slope. So for every torsion-free coherent subsheaf on X, you can define the slope as the degree of the sheaf E measured with respect to this ample divisor, and then divide by the rank. So once you have this notion of slope, you also have this notion, a notion of semi-stability. So a sheaf is going to be semi-stable if it does not contain any subsheaf with bigger slope. And then we have the classical Harder-Narasimhan filtration. So for any such sheaf E, you can find a filtration by subsheaves with the following property. So the quotients are semi-stable and they have decreasing slope. So this filtration is unique, and it has some very nice properties. So some things that you can prove easily using the slope, the properties of the slope, is that if you look at this filtration, then the slopes of the EIs, they are decreasing. And on the other hand, if you look at their degree measured with respect to H, then what happens is that you start with the E1, and then the degrees increase until a certain point, and then they start decreasing. So they increase as long as the quotient has positive slope, and then they start to decrease. So a theorem that was proved by Miyaoka, Boss, Bogomolov, McQuillan, so I'm just giving credit to all of them here, says the following, that if you take, we are going to apply the Harder-Nurseman filtration to the tangent bundle, and let's assume that the degree of the tangent bundle with respect to this H is positive. And then let's consider the sheaves EI, E1, E2, until as long as their degree is increasing. So we consider E1 up to EI, where the degree of EI is the maximal one among the subsheaves. And then the striking result is that each of these EI, in fact, define a foliation and more an algebraically integrable foliation. And moreover, the leaves of these foliations are rationally connected. So these are the ideas that you can use to prove Miyaoka's criterion. It's not hard to, I mean, actually I put assumptions here that are a bit stronger than necessary. So for instance, instead of working with the tangent bundle, you can start with a foliation, and then the same conclusions hold. And now let me tell you about a more recent development in this theory. So the theory of semi-stability, slope semi-stability with respect to an ample divisor is very useful, but it's not flexible enough to deal with some problems in birational geometry. So recently, there has been some developments, and instead of looking at slope with respect to an ample divisor, one can look at slope with respect to a movable curve class. So instead of measuring the degree with respect to an ample line bundle, what one can do is to take a movable curve class. So this is a class of 1 cycles inside the closure of the cone generated by movable curves. So these are curves that can deform to sweep out a dense open subset of X. And then you can define the slope with respect to this movable curve class, and then again you still have a Harder-Nurseman filtration, and now a recent theorem by Campana and Pound showed that the same thing holds, that if you take the first pieces of the Harder-Nurseman filtration until the degrees gets maximal, then they are all defined algebraically integrable foliations, and the leaves are still rationally connected. Okay, so now, if we want to then use this criteria of algebraic integrability, then one has to find conditions that guarantee that these assumptions are verified. And one possible way to have these assumptions verified is, for instance, to have the first Chern class of the foliation to be ample. So this is what we call Fano foliations. So this. So Stéphane and I started to study Fano foliations, and then we've been doing this for many years now. And so let me define them formally. So we start with a foliation on a complex projective manifold, and first we define its canonical class as minus the first Chern class of its the foliation, or the tangent bundle of the foliation. Tangent sheaf of the foliation. And then we say that the foliation is Fano if this anti-canonical class is ample. And in this case, one can define the index of the Fano foliation as the biggest integer that divides the anti-canonical in the Picard group of X. And so the first thing that we notice is it's very easy to see that the index cannot be arbitrarily large. There must be, once you fix the dimension X, the variety X, there must be a bound on the index. And this is very easy to see, because if you have a foliation, so if you have a subsheaf of the tangent bundle, then you can dualize, and you can think of this foliation as a non-zero section of a certain sheaf of twisted differentials. So this n minus r, the dimension of n, minus the rank of the foliation, is what we call the codimension of the foliation. And you see from this formula that so the index cannot be arbitrarily large. At some point, we don't have any global forms there. And then, so let's see, for instance, what happens in a very easy example, the case of Pn. So if you have, then you can, by looking at this cohomology group, so these cohomology groups are all known for Pn, these are Bott's formula, then you can easily check that the index must be at most equal to the rank. And so it should be interesting to know what happens in the limit case when the index is equal to R. And in this case, Cerveau-Deserti showed that this happens exactly when the foliation is given by a linear projection. So the sheaf is a direct sum of all ones, and so I just put a picture here. So what you have is a linear projection. It's induced by a linear projection from Pn to some other projective space. Now, one can look at the next case and ask what happens then when the index is one less. And again, these have been classified by Loret, Pereira, and Touzé, and they show that there are two types of foliation with index R-1. So one is, again, it's algebraically integrable. It's induced by a rational map to a weighted projective space defined by a quadratic polynomial and n minus r linear forms. So again, this is algebraically integrable. And then there's another type of the index R-1 foliation, which can be constructed as follows. You start with a linear projection to, again, a projective space, but now the codimension of this linear projection is one less than the rank. And then you take, on the image projective space, you take a global vector field, consider the foliation induced by this global vector field, and you just pull it back to Pn. And so this is the second type of foliation. So remember, the first example that I gave you, I showed you that on P2, if you take a general vector field, that was not algebraically integrable. We saw an example where the leaves are exponential, given by exponential functions. And so we see that already in the when the rank is, the index is R-1, then we already get some non-algebraically integrable foliation. Okay, so in the general case now, so this was for Pn. So now what happens in general? So first, in 2008, together with Chandra Kovac, we proved what could be called as the Kobayashi-Yochai theorem for foliation. So we proved that in general, the index of the foliation is always bounded by the rank, and if the index is equal to the rank, then we are in the case of Pn. Okay, so now it's interesting then to look at the next cases, and so again, in analogy with the theory of Fano manifolds, we define a del Pezzo foliation as a foliation whose a Fano foliation whose index is R-1, so it's one less the upper bound. Okay, so then we started a systematic study of del Pezzo foliations. So the first theorem that we proved is an algebraic integrability criteria for del Pezzo foliation. So we proved that if X is different than Pn, so we saw that in Pn there is a del Pezzo foliation whose leaves are not algebraic. But what we prove is that this is the only possible case. So if X is different than Pn, then any del Pezzo foliation on X is algebraically integrable, and the leaves are rationally connected. Okay, so and then we started to work on the problem of classifying del Pezzo foliations, again very much inspired by the classification of Fano manifolds with high index. And so I just want to give you a sample of the type of theorem that we proved. So this is the classification of codimension 1 del Pezzo foliations. So we suppose that the rank is n minus 1, that it's a del Pezzo foliation, and then we proved that, well, if the Picard number is 1, then either x is Pn, and in this case we have already discussed and described the del Pezzo foliations, or x is a quadric hypersurface in Pn plus 1. And in this case, again, we show that the only del Pezzo foliation that can occur on a quadric is given by a pencil of hyperplane sections. Okay, so this is a sample, but in fact, we proved classification results similar to this one, but going in various directions. So, for instance, one important point is that, as I said, for most of this talk, I'm going to be talking about smooth projective varieties, but actually much of our theory actually is developed also for mildly singular projective varieties. So we actually have a classification of codimension 1 del Pezzo foliations on some mildly singular varieties. And if you impose some restrictions on the singularities, we obtain the same classification as before, but allowing for one more case, which is a cone over a surface, something that's very well understood. Sorry, let me just go back here. I forgot to say something. So this was in the Picard number 1 case. So if the Picard number 1 is at least 2, actually we prove that X must be a PK bundle over P1. And moreover, we give a precise classifications of the projective, of the possible vector bundles E's that may occur, and a complete description of the F's that appear in this case. And again, in the mildly singular case, we get exactly these 2 cases plus a possibility of being a certain cone. Then we also looked at, now we looked at the next case, foliations with index R minus 2. So again, in an analogy with the case of Fano manifolds, we call this Yochai foliations. And again, we obtain a classification, but now there are much more examples. And now what I want to say a little bit is our classification results for del Pezzo foliations with arbitrary rank. So, so historically, most of the theory of foliation has been developed for either foliations by curves on varieties or codimension 1 foliations. But now we developed some tools that also work in an arbitrary rank, but in order to get a classification, we actually had to impose some restrictions on the singularities of F. So I don't want to be too precise here, but so let me say something here. Okay. So first of all, so one result that we proved is a classification of algebraic leaves of del Pezzo foliation. So we have a complete classification of all possible, so we already know that if you are not in PN, then del Pezzo foliations have algebraic leaves, and we completely classified what leaves can occur. And then we started to study, in order to classify, we started to study properties of these foliations, and then we had to restrict our attention to some mildly singular foliations. And here I just want to say that there are notions of canonical and log canonical singularities for foliation. So this is very much in the spirit of what Chen Yang explained to us today. So there are notions, and canonical and log canonical seem to be the important notions to work with if you want to do birational geometry using foliations. And so, for instance, one important property that we proved is that if you have a Fano foliation of arbitrary rank, and here I'm not restricting to del Pezzo, any Fano foliations which is algebraically integrable and has log canonical singularities has this very special property that there is a common point in the closure of every leaf. And so this is definitely not true if you drop the log canonical assumption, or if you drop the Fano assumption. So this was a key property that we used in all our proofs. Okay, so let me say something about one reason why one may want to study Fano foliations. So there is this conjecture to Skovsky, which as far as I know is not, there's no proof nor negation of it yet, is that if I have a Fano manifold with Picard number 1, then the tangent bundle is stable. So this notion is weaker than the notion of K stability that we heard this morning. But so let's go back to our Harder-Narasimhan filtration. So assume that the tangent bundle of X, of our Fano with Picard number 1, is not stable. Then in this case, we can normalize the slope to be the index of the foliation divided by the rank. And we take a maximal destabilizing subsheaf of Tx. So a maximal destabilizing subsheaf is that first piece of the Harder-Narasimhan filtration, which has the biggest possible slope. Then it is a Fano foliation, and its index is somehow large when compared with the index of T. And so this theory of foliation may have some application either to prove or to refute this conjecture. Okay, but this is just a side remark. So let me go back to what I was talking about. I just want to remind you this theorem that was some slides back. So if you have a del Pezzo foliation on a complex projective manifold X, then either F is algebraically integrable, or our ambient variety is Pn, and our foliation is a linear pullback from a foliation with numerically trivial canonical, or with trivial canonical class in a projective space. And so, and as I said, we studied also, we classified Yochai foliation, so those are with rank, with index R-2. And again, what we observed is that there were some cases, many cases, when the foliation were not algebraically integrable, but they were not so far from being algebraically integrable. So we started then to study the relationship between positivity of the foliation, which here is measured by the index, and algebraicity of the leaves. And so first let me introduce an invariant which measures the algebraicity of the foliation. So if you start with the foliation on X, then if you give me if you take a general point, you can look for the largest algebraic variety passing through this point that is everywhere tangent to the foliation. So if you do this for a general point, you actually do get a subfoliation on X, which is algebraically integrable. And so it comes from a dominant rational map with connected fibers. And then this foliation F is invariant by this rational map. So it comes as a pullback of a purely transcendental foliation on Y. By purely transcendental, I mean that there is no positive dimensional algebraic variety on Y that is everywhere tangent to G. And so we define the algebraic rank of the foliation to be the relative dimension of this dominant rational map. So this is the dimension of the biggest algebraic variety through a general point that is everywhere tangent to F. Okay, so what we proved is that, so we want to find results that invariants measuring the positivity of the tangent bundle that bound this algebraic rank. So what we proved was the following. So if you have a Fano foliation of index I, then the algebraic rank of the foliation is bounded from below by the index. So this is and moreover, the algebraic rank is equal to, if the algebraic rank is equal to this lower bound, then we are in the case of Pn, and our foliation F is the pullback under a linear projection of a foliation with numerically trivial canonical class. Okay, so now notice the following. So the tools that we used are the tools of, for instance, the Hardenism and filtration and the theorem of component bound. But remember that applied to movable curve classes. So for movable curve classes, we actually don't need to assume that the anti-canonical bundle of the foliation is ample. So let me define, we are allowed to define sort of a modified index which measures, again, the positivity of a foliation, but it measures in a different way. So I define this modified index in this way. So we can write our anti-canonical, because our anti-canonical we can write it as a multiple of something ample plus some effective real divisor, and the biggest t that appears as a coefficient, which is in general a rational number. In general, could be a real number, but it turns out to be a rational number that realizes this kx in this way. And so we can actually replace in our theorem not only, so this criteria, this bound doesn't work only for Fano foliations, but in general, if you have a foliation whose anti-canonical bundle is big, then this modified index is going to be positive. And the algebraic rank, again, is bounded from below by this generalized index. And again, the bound is attained exactly in the case of Pn and the foliation given by a pullback under a linear projection of a foliation with numerically trivial canonical class. Okay, so talking about the foliations with numerically trivial canonical class, now I want to just discuss some parallel developments in the area. So first of all, there are structure results for foliations with numerically trivial canonical class. So this is a work of Loré Pereira. It's a series of various different papers. And more generally, and this is very remarkable, there has been an algebraic integrability criterion by Stéphane Druel for foliations with numerically trivial canonical class. And here it is important that I mention that this criteria is for singular varieties. And this is very important because this was the key ingredient to the recent structure theorem for singular projective varieties with a numerically trivial canonical class, which extends the Beauville-Bogomolov decomposition theorem. So the classical Beauville-Bogomolov decomposition theorem says that if you have a smooth projective variety with numerically trivial canonical class, then after taking finite étale cover, this is a product of tori, a Calabi-Yau, and irreducible symplectic manifolds. And very recently, this has been generalized for singular, mildly singular projective varieties. And as I said, the key ingredient is this algebraic integrability criterion by Stéphane Druel. And okay, some other parallel developments is a recent theory of a minimal model program for foliations. So let me just say a few words about this. So in the end of the 20th century and beginning of this century, with works of Prunella, Mendes, McQuillan, and others, there has been a birational classification for foliation by curves on surfaces. And then people started to try to develop a minimal model program for foliations of higher rank, arbitrary rank and arbitrary dimension. This turns out to be very difficult. So some of the difficulties that one encounters in higher dimensions is the failure of Kawamata effect vanishing, abundance, resolution of singularities, which are very fundamental in the minimal model program. So these are the difficulties, but let me tell you something, something in the positive side. So in the positive side, we have, and this is just for foliations on threefolds, for higher dimensional varieties. I don't think this is much is known. But for threefolds, there is a reduction of singularities. One does not have resolution of singularities, but we have a reduction of singularities. And here, the right notion to look at is the notion of canonical singularities. And also recently we've had by Spicer a cone theorem for rank 2 foliations on threefolds. So this is this program, this minimal model program, foliations, is something that seems to be still very far away. But one may hope that that Fano foliations, as well as foliations with numerically trivial canonical class, should play an important role in this theory. And for this reason, it's actually important, since the minimal model programming, we know that we have to deal with singular varieties. It is important that this theory that we have been developing actually it holds for mildly singular varieties as well. Okay, so I think I just went a bit fast, but this is all I wanted to tell you. Thank you very much.
Thank you, Carolina, for this beautiful lecture. Any questions for her?
So, is the foliation G on your bound for the rank, on this result bound in the rank, the foliation G you get is purely transcendental? Or?
No, we do have results when we can guarantee that actually, so if the rank, so we have a bound on the algebraic rank, but if, so let me just go back. So we have this bound on the algebraic rank. So the G here is purely transcendental, just by definition. So this is but in the next case, if you assume that the algebraic rank is one more, is this index, the modified index plus 1, we can actually prove that that is again the. It is, sorry, let me say how I can say this. So this, we can prove that in this case, maybe let me just say that we can, under certain conditions, we can actually prove that something that has numerically trivial canonical class actually has positive algebraic rank under some assumptions on the index and the rank.
Any other questions? Okay. If not, we thank Carolina again.